We're looking at some data, and this is from Brandon in my third period. And what we did is we had students enter into the calculator in a column, and then they recorded how fast they could do that. And so when he did 10 digits, it took him 3 seconds. 20 digits, 8. 30 digits, 10. 40 digits, 12. 50 digits, 14, and 60 digits, 16. Okay? And the question is there a relationship between the total number of digits and the time required to enter it? So when we're doing a regression, we're trying to establish a model. So the easiest way to do this is to put this in your calculator. Now, some students are tempted to put in the task number, but this is not really the x. Our explanatory variable is the number of digits. So that's our x. All right? And then what we're recording here is the response, which is the time. And I should really write on here time in seconds. Always good to label your axes. And digits. Alright, so I'm going to go ahead and enter this in the calculator, and you hit Stat, Edit, and my lists are clear, so I'll go 10, 20, 30, 40, 50, and 60. Then I can go to the next set, 3, 8, 10, 12, 14, 16. Okay. Now I'm going to go ahead and see if the scatter plot I created here matches the one I drew. It's a good idea in case I misentered some of the data in my calculator. So I went second stat plot, make sure the plot's turned on. List 1, my explanatory, and then list 2 is my response variable. I can hit graph. And normally it's messed up, so I have to hit zoom 9 for zoom stat. And yeah, that looks a lot like the graph I drew. So that's good. Now I could run the regression analysis. So I'm going to hit Stat again, and we want line reg, because L is for linear and reg is for regression. Alright, so I'll come down here, or I could just press 4. This calculator gives me a table, so it's making it very clear there's my X list and my Y list. It defaults to list 1 and list 2. If I want to change it, I can use second list to pull up the list numbers and do that there. But I don't need to do that, so I'm going to hit Calculate. And you can see that my model is, there's my slope, 0.243, and my y-intercept is 2. So I can say 0.243 x plus 2. And put a little y hat, because that means we're making predictions. This is based on data, and it's not based on a population, so it's a statistical analysis. So my model, we really like to write everything in context. So instead of using y, I'm going to use time. And I have equals 0.243 times the number of digits plus 2. There's my model. Kind of curvy around. Sorry about that. Alright, so there's my model. Now I can make predictions with the model. For example, predict time for 35 digits. Well, what I would do is just put 35 in there. So the time would be 0.243 times 35 plus 2. Put that in my calculator, 0.243 times 35. I always like to do that first, plus 2. I'm predicting 10.5 seconds. Which, if you look at it, for 25, this 5 digits, look, right there, it would be about 10.5 seconds. That makes sense. So this looks like a very good model. How good is the model? So how good is model? We use basically something called Pearson's correlation coefficient. Which is R. Alright, so looking at my data, let me go back in Calc. And I'm going to go to line reg. Dun, 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 dun. Now, wait a second. I need R. When my calculator doesn't show it, what that means is someone either changed the batteries or they cleared the memory. So I'm going to have to hit second catalog, second 0, and then scroll. Thank goodness this starts with D instead of some letter later in the alphabet. I find diagnostic on. Alright, there it is. Hit enter and enter. Okay, now when I hit stat calc 4, voila, I have R, which in this case is 0.980 after rounding. In this case, 0.980. Is 0.980 good? It's pretty darn good, actually. This is strong and positive. Does that make sense? That's the positive direction? Yes. Your slope should match your correlation coefficient. My slope is positive. My correlation coefficient is positive. All right. And how do you know what's strong and what's not strong? Well, basically, if you go above 0.8 to 1, strong is 0.8 to 1, or negative 0.8 to negative 1. All right, that's what strong is. Less than, say, 0.4, somewhere around there. And you can basically use your judgment. There's no hard and fast rule for it. Okay, so that determines the strength. Now, since I have a very good correlation, my question is, I can go ahead and use it for predictions, right? Where can I predict? Well, I have to be careful. We want to avoid something called extrapolation. All right? The extra means outside. All right? Kind of like extraterrestrial. If I had a little Martian here, here's his little helmet and his little antenna, and he's walking around. My little Martian is an extraterrestrial. That means he's outside of the Earth. In extrapolation, we go outside of our data. All right? Extrapolation is bad. All right? So don't use model. If X is outside of the range, and I'm calling range loosely, from 10 to 60. All right? So I don't want to extrapolate at 0. Well, why doesn't that make sense? If I use this model for 0 digits, what does it predict? It predicts that Brandon will need 2 seconds. So here's an example of extrapolation. The model predicts Brandon needs 2 seconds to enter 0 digits. Does that make sense? No. Doesn't make sense. All right, so don't extrapolate. That's the main idea. All right, now another thing we can look at is something called the coefficient of determination. It tells us what percent determination. It tells us the percent of variability that is attributable to the model. We call it R squared as well. And in this case, from my calculator, if I bring it back up and I look, R squared is 0.960. We can say 0.9601. All right. So what does that mean? This tells me the percent of variability accounted for by the model. All right? So in this case, I can say 96.01%. It's a little precise, but okay. Variability in Brandon's times are explained by the model. and 3.99% of the variability is unexplained. All right, one last thing I want to kind of talk about is how to interpret that slope. All right, and we'll do this by looking at some different sets of data from my other classes. So for one class, I had someone who had 7, 9, 15, 16, 26. So this was my third period, this one was my 8th period. So if I were to graph these, 10 is at 7, then 9, 15, which is up here, 16, 20, which would be right here, and 26, which would be all the way up here. So this is the graph of my other set of data, and you can see that this line would be different. If I enter in my data, stat, edit, don't need to redo the first column, that's already right. So we got 7, 9, 15, 16, 20, and 26. Stat calc, 4. You can see I have a slightly different equation. For this one, I have y equals 0.39 plus 2.6. So it's actually predicting a higher y-intercept, and it has a higher slope. Why the higher slope? Does that mean they're faster? No, actually it means they need a bigger piece of time for every jump in digit. So if I were to do this, for every extra digit, pretend there's an X there, I need 0.369 seconds. All right? Here, this one predicts for every extra digit, I need 0.243 seconds. I'll do one last set of data from my 6th period. And they had numbers of 6, 10, 12, 11, 15, and 16. All right, so entering that data. Oh, actually, look at the correlation here. This correlation's a little lower, which kind of makes sense. Let me go ahead and plot this. 10 is 6. Then we had 10, 11, so it actually dropped down. Maybe they were getting better. 15 and 16. So it's right here on the same point. All right, stat edit. So 6, 10, 12, 11, 15, and 16. So when I go stat calc, you can see my correlation actually dropped a bit. It's down to 0.943. Explained variance for this person is 89.5%. So basically 10.5% of the variance in their time is unexplained. All right? And for them, if I were to write the equation for the green line, y equals 0.18 3x plus, and they have a big y-intercept, 5.3. Interesting. So they kind of start, looks like they need a little extra time, but once they get started on entering the digits, they're probably pretty fast. So that is correlation in a nutshell.